Hello, so we are going to continue studying group actions. So we're going to suppose that we have a group G acting on a set A. And so this is mostly section 4.1 from the textbook, which starts off with a review from section 1.7 and material from section 2.2, which we already covered, so that makes that part kind of silly, but I'll just point out by stating the first major proposition they point out is the proposition 1 in the textbook, is that there is a bijection or a correspondence between actions of G on a set A, so the set of all actions, and the set of homomorphisms from G to the symmetric group on A. So I had already stated this bijection in a previous video by pointing out that given an action, the associated homomorphism is the one that sends G to sigma of G, where sigma of G A is just G dot A. So we went through the proof that this was in fact, for any element G, this was in fact a permutation, and this was a multiplicative map, and so this isn't a homomorphism. And vice versa, given any such homomorphism, it gave rise to a group action. I guess in order to state these things carefully, we should probably label the group action by alpha. And the corresponding group homomorphism is sigma of alpha. And so, the remaining thing that one would have to show is that this correspondence is in fact a bijection, which means that if I take a group action, I create a homomorphism. When I go backwards, the resulting group action is the one I started with. That's actually not that hard to show. Because remember, the reverse direction was given a homomorphism. The corresponding group action we define that depends on that homomorphism, so I'll use this subscript to denote that dependence, was just apply this homomorphism to get a permutation in A, and then apply that permutation to this little element. You might remember that's how we define the reverse direction. Given this homomorphism, this was how you define the group action. So my point is, suppose we start with the group action. Let's do our construction to create this homomorphism, sigma sub G, sigma from G to SA. Now go backwards. G dot sigma of A is sigma G of A, which is sigma sub G applied to A. But what is sigma sub G? It's just G dot A. So we see that our constructions are inverses of each other in one direction. In other words, given any group action, if you construct this group homomorphism to the symmetric group and then create a group action from it, you actually get the group action you started with. Similarly, I leave it to you, you could check the other direction. Given a group homomorphism from G to this symmetric group, you can construct a group action. Let's actually do that. So now I'm starting with my group homomorphism. I've created my action. G dot sigma A is sigma G applied to A. Now I need to go backwards. I need to define my new homomorphism. We're going to call this action alpha. What's sigma of alpha? Of G, it's going to be this permutation that sends A to G dot sigma of A. In other words, it permutes according to what the action says it should do. but the definition of our action is that should be sigma g of A. So this is a complicated way to say that no matter what, if you take these two constructions either direction, you get back to where you started. So these two constructions undo each other, which means this is in fact a bijection. So equivalently, a action is essentially the same thing as a homomorphism from G to any symmetric group. And so it's said that the action is faithful. Let's ignore all concepts of relationships here. This is a mathematical definition of faithful. If the kernel of the action is trivial. Or equivalently, if this homomorphism is injective. So right now I defined it in terms of this group homomorphism, but what does that mean in terms of the action? It means that if you look at the set of all G that have the feature that G dot S is S for all S in your set A, remember this subgroup called the kernel of the action, the only thing you get is the identity element, which in this video apparently I've decided I'm going to use E for. When this happens, sigma is called a permutation representation. Why? Because you've just represented your group as a collection of permutations in the group operations composition. And in general, well, faithful representation. In general, this is always true. You call this a representation because you're representing your elements as permutations. Later, when we talk about representation theory, we'll do something similar, only we will replace this group on the right with a matrix group. In general, the concept of representation theory is representing the elements of your group as elements in some other sort of concrete group. So what do I mean by concrete? Well, the advantage of permutations is that they can be presented by a computer using finite data. It's easy to write down a permutation and to compute it with a computer. It's easy to write down matrices and compute matrix multiplication with a computer. So usually, with representation theory, you want groups that are concrete and easy to manipulate. And by easy here, I mean even though the size of the group is large, calculating the multiplication for two elements in the group is relatively easy to do. I mean, calculating multiplication for an arbitrary group is hard because you need the entire Cayley table in order to do it. There is that factor result from section 4.2 that I'm going to assume without proof because it comes from, it's sometimes mentioned in the undergraduate course called Cayley's theorem. Remember, G always acts on itself by G dot A is just multiplication, left multiplication. According to the theorem we just proved, this means that there is in fact a permutation representation from G to the symmetric group S of G. And one can check that the kernel in this case is in fact trivial. So it's in fact a faithful permutation representation. And so Cayley's theorem says that every group is isomorphic to a permutation group. And a permutation group is any subgroup of any symmetric group on a finite set. Well, an arbitrary set, I should say. And so the historical context and importance for Cayley's theorem is that when Galois originally introduced the concept of group, the definition of group used to just be a collection of permutations closed under composition. And you can actually prove a version of the subgroup criterion that says if you have a finite subset of a group that's closed under multiplication, then it's actually a subgroup according to our modern definition of group. In other words, you actually get the inverses for free. So their definition didn't originally include inverses, but it turns out you get the inverses for free. And it was only later that they realized they needed to include it as a separate axiom. And so Cayley's theorem says that it turns out every group is in fact a permutation group. So there really is no distinction between the two definitions. The modern abstract group is the same thing as the classical one that you originally started with. That being said, at some point it is fun to look at examples. So let's actually look at some examples of permutations. We've already talked about how Sn acts on the set of the positive integers 1 through n through the obvious action where you just apply the function. This is just the standard action, and it turns out the resulting permutation representation is the identity function. Which is not that exciting. I mean, you can check through the definitions. For instance, let's just look at S3, and let's let sigma be 1, 2, 3. Well, how does sigma act on 1? It sends it to 2. How does sigma act on 2? It sends it to 3. How does sigma act on 3? It sends it back to 1. Well, let's call this G, actually. So what's sigma of G? Sigma of G of 1 is 2. Sigma G of 2 is 3. Sigma G of 3 is 1. Oh, look, sigma of G is just 1 goes to 2, goes to 3. So proof by example is not actually a proof, but it's a good concrete way to get an understanding for why this would conceivably make sense. But then you check the definition, you see exactly why it should make sense. It's because this is the definition of the action. You see that sigma sub G of k is defined to be G dot k, which by the definition of our action is just G of k. So you see from right here that sigma of G is just the same as G. The complication and why this is hard to understand is because I'm conflating notation here. The reality is that both these elements are in the same set because they're both permutations in Sn. I won't always do the examples from the book, but sometimes I will. In this case I will because it's a geometric picture and sometimes it's worth going through the picture. So I will do example 2. And I'll leave you to check example 3, which is similar. And so they want D8 acting on the square. Note, in this textbook, D sub 2n acts on the n-gon. And so this is the symmetries of the n-gon. And so there's lots of symmetries. But you might remember that this group is generated by a rotation and a reflection. And the rules is that the rotation has order 4, the reflection has order 2, and if you rotate and reflect, it's the same thing as reflecting and then rotating in the opposite direction. And here we're going to assume that we're rotating clockwise 90 degrees. and that the reflection is going to be across this vertical line. So then let's see what happens when you apply rotate. Rotation sends 1 to 2. Rotation sends 2 to 3. Rotation sends 3 to 4. And rotation sends 4 to 1. So you see the corresponding permutation for the rotation operation is 1, 2, 3, 4 as a 4 cycle. Similarly, if we look across reflection across this vertical line, we see that reflection is going to interchange 1 and 2 and 3 and 4. And so this ends up being the image of our homomorphism for these two elements. In fact, you can check that the D8 under this homomorphism is actually the subgroup generated by these two elements. And you can do that if you want by actually doing the multiplication table. Sometimes in the undergraduate modern algebra class, I actually have them do this calculation and then point out this symmetry as an example of an isomorphism. So it's sometimes fun to do that, but I won't do that today. Instead, I will note what is the kernel of the entire action. Well, that's the symmetry that fixes all 4 vertices pointwise. Well, clearly the only one that does that is the identity, and so this action is faithful. Also, the other observation we make is that the stabilizer of any vertex, let's say 1 in this case, which symmetries are going to fix the vertex 1 pointwise? Well, this line of symmetry, reflecting across this line of symmetry in the identity transformation will do the trick. Of course, you'll have to think hard to figure out exactly which reflection it is, but it's one of the reflections. And we see none of the rotations will work. On the other hand, if you actually take the stabilizer for set of 2 of the vertices as a set, not pointwise, then you'll get more. You'll actually get an interesting subgroup. Why? Because now the 180-degree rotation is actually in the group too.